You improve the metric a little, but is it real? This video shows a simple way to check whether the improvement could just be luck. You shipped a small accuracy bump, and someone asked for significance. You want a simple test that does not assume a normal distribution or large samples. By the end, you will know how to run a paired permutation test in Python and decide if that tiny gap deserves trust. I'm Professor Pi, teaching AI foundations with simple Python. In production, you often compare two models on the same test set. The pain is that small gains can be noise. A paired permutation test answers the question, how likely is this gap if there were really no difference between models? Practitioners reach for it when data is limited or when typical parametric assumptions are shaky. Intuitively, the test asks what outcomes would look like if model labels were exchangeable. For paired comparisons, we flip which model wins on each example to simulate the null. A concrete mini-example is a tiny accuracy gap between two classifiers on the same 10 examples. Strengths include minimal assumptions and an exact answer when you enumerate all sign patterns. A weakness is combinatorial cost if many examples disagree. We will build a short pipeline. First, compute the raw accuracy gap. Then, make per example win-loss entries. Next, run a Monte Carlo sign flip test for a quick p-value. Then do an exact enumeration over disagreements when possible. Finally, run a larger precision test and make a keep or drop decision. These steps use paired differences and sign flips as the core idea, so the code feels less scary. This snippet computes a tiny accuracy gap between two models in NumPy. We create a small binary label array, y, and two model predictions, a and b. Accuracy is the fraction of exact matches between predictions and labels. We subtract model A's accuracy from model B's accuracy to get gap, a quick effect size. This gives us a concrete, comparable number without any randomness or external files. The printed gap quantifies how much better B appears on this toy set and becomes the observed statistic we compare to a null distribution later. Next, we turn predictions into head-to-head outcomes. This snippet converts predictions to per example wins and losses for model B. We build correctness arrays, CA and CB, where 1 means the model got that example right. The array diffs equals CB minus CA. So +1 means B beat A, -1 means A beat B, and 0 is a tie. Counting positive entries gives wins. The number of examples where B improved over A. This pairs outcomes per sample, which is the foundation for a valid permutation test. The printed wins shows how many head-to-head victories B has, and explains why we focus on non-zero entries next. Now we run a quick Monte Carlo permutation to get a preliminary p-value. This snippet approximates a permutation test with NumPy sign flips to get a preliminary p-value. The statistic d-obs is the average paired improvement from diffs. Under the null that models are equally good, each per sample gain could swap sign. So we sample random sign matrices with numpy.random.choice. Multiplying and averaging gives a null distribution for the mean difference. We compute a two-sided p-value as the proportion whose magnitude exceeds the observed difference. Increasing the number of rows from 200 tightens the estimate, but takes slightly longer. The printed p-prelim compares observed improvement to a random chance benchmark and helps you spot whether a full enumeration is worth doing. Next, we tighten the null by enumerating only the disagreements. This snippet tightens the null by exact enumeration over disagreements using itertools. We isolate DC, the non-zero paired differences where models truly disagree. Using itertools.product, we generate every possible sign pattern for these pairs under the null. Multiplying by each pattern and averaging yields the exact null distribution of mean improvement across disagreements. We then compute a one-sided p-value for B being better. One-sided testing improves power when direction is pre-specified. Two-sided is safer if not. The printed P1 shows how often chance would produce at least the observed directional gain, and gives an exact answer when the number of disagreements is small. Finally, we run a higher precision two-sided test and make a decision. This snippet runs a higher precision two-sided test and makes a simple decision. We draw many sign flip samples with NumPy to reduce Monte Carlo noise and build a stable null distribution. The two-sided P compares the observed effect against both positive and negative null extremes. With alpha fixed at 0.05, we choose keep B if the effect is significant and positive, keep A if significant and negative, else uncertain. Increasing samples lowers variance but adds time. Decreasing does the opposite. The printed decision communicates whether the tiny gap looks real or likely noise, and gives a clear action for model selection. This toy pipeline maps directly to a real model comparison scenario. If you compare two ranking models on a held-out test set of a few hundred queries, compute per query wins as we did, then run the permutation logic. If disagreements grow large, switch to Monte Carlo sampling or approximate methods to keep runtime practical. Recap: it is a paired permutation test that compares models by flipping per example wins to build a null. Use it when you have a paired test set and want a non-parametric significance check for small effects. One caveat is compute cost when many disagreements exist, which may require Monte Carlo sampling. Next step: tune the number of sign flip samples for the Monte Carlo stage to balance precision and runtime. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.